The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our last speaker is Jason Weiss. He kicked us off, so we're going full circle. I know there's some new folks in the audience. I'll introduce Jason one more time. Jason is a fellow of ACI, and he's the professor and director of the Pankow Materials Laboratory at Purdue University. Earned his bachelor's degree from Penn State University, and his master's degree and PhD from Northwestern University. Jason received many ACI awards, the Walter P. Moore Jr. Faculty Award, ACI's Young Member Award for Professional Achievement, ACI's Wasson Medal, and so on. And so Jason's talk today is titled, Using Internal Curing to Mitigate Early Age Cracking and Increase the Performance of Reinforced Concrete with Respect to Corrosion. Please help me, Jason Weiss, or help me welcome Jason Weiss.
Thank you very much, Anton. What I really want to do today, as mentioned, is I'm really going to try to start to relate what we're trying to do with internal curing in terms of keeping cracks out of the concrete with some of the implications that's going to have on long-term corrosion. What I think we're all sort of in agreement that there's potential issues when we start getting cracks in the structures. This sort of, I think, drives this point home that currently there's over 100,000 bridges that have transverse cracking that are exhibited. 62% of the DOTs consider early cracking to be a major problem, and a lot of this cracking is occurring long before these bridges are ever even trafficked. And the real issue here is that the cracks are going to shorten the service life, they're going to increase the maintenance costs, they're going to accelerate the corrosion, and they're going to mean that we're going to be out there replacing these decks more frequently than we really need to do. So the question is, can we do something early on to get substantially more service life out of the decks that we're looking at? So what I really want to try to go over today is I want to really try to hit 4 main points. I want to understand a little bit about why the low water to cement ratio, higher cement content mixtures may be more susceptible to cracking. These are the high performance concretes that we're talking about. We want to understand why they're more susceptible to cracking. And we want to understand how this, though, can be combined with internal curing to reduce this cracking potential, especially at the very early ages. This is a technology that's really going to help out during the really early time where the concrete is very susceptible. Understand, and I'm going to skip through this very quickly, this part here, but to understand how internal curing helps us with the transport properties as well. And then what we're really looking at is combining both of these issues together. Can we reduce the cracking, but also reduce the transport properties, and what are the impacts on service life? And that's really where I think we really start to see the benefits. So what I want to do very quickly is I want to talk about shrinkage and stress development, and I want to talk about this for the idea of trying to motivate why lower water to cement ratio, high cement concretes may be more prone to early age shrinkage cracking. And in order to do that, I think it's important that we take a little bit of a look at what are some of the main factors that drive the shrinkage and the stress development in the system. Now, I'm not expecting everybody to understand all the equations and the variables and to rederive this at the end, but the basic idea is we've got a sample that's a specific length. If it wasn't restrained, it would shrink, it would get smaller by a certain amount. The subgrade, if it's a pavement, the bridge deck, the girders, if we're in a bridge system, they're going to restrain it, and it's effectively like pulling on the concrete retention. Now, if we just do this, this green line here is nothing more than Hooke's law. It's stress, modulus, and the shrinkage. Stress, modulus, and the shrinkage. However, there's an additional effect that comes into this, which is really, really beneficial at early ages, and this is viscoelasticity. This is relaxation. This is stresses that are being worked out of the system at very early ages. So you can see that the stresses are substantially reduced by this viscoelasticity. Now, I think that this is a really important point to bring out here, because in this particular case, viscoelasticity is helpful to the system. Creep, for example, relaxation is a good thing because it helps to reduce the stresses in the system. So by the time we start to formulate this equation, we've started to see we've got shrinkage involved, we've got modulus involved, and we've also got the creep involved in the system. Now, if we think about the case that I was talking about before, where we go to a lower water to cement ratio system with maybe a slightly higher paste content, we know that the modulus is going to go up. We know that the creep is going to go down. Both of those factors, right? If we have less creep, the stress goes up. If we have a higher modulus, the stress goes up because we have to pull the system with more force to bring it back to that zero displacement. In addition, the higher performance concretes tend to be more brittle, right? But you may say, well, but I'm going to make it up because when I look at this, I'm going to have lower shrinkage in the overall system, right? So you can go to a textbook and you can say, well, if I look at the shrinkage, it decreases as a function of water to cement ratio. But what I'm going to point out is when we look at restrained shrinkage cracking data, we have the age of cracking here plotted against the 28-day strength. The higher the strength, typically the more susceptible the concrete is going to be to cracking. Now you may say, well, why is this if we're decreasing the shrinkage? One thing that's very important when we go back and we start to pull some of this data out of older literature, this is done with the ASTM C157 test. This is done with the free shrinkage test that starts at 24 hours. And what I really want to drive home here is when we're talking about high-performance concretes, just because you took 24 hours between placing the concrete in the forms and coming back to start the measurement, doesn't mean that the concrete also took that time off. So if you measure the autogenous shrinkage that's occurring during that time, what you can see is this is the amount of shrinkage that's being missed out on, all right, while the concrete is in those forms. And what I want to argue and what I want to put forth is this is the autogenous shrinkage that's occurring throughout the cross-section. So it's uniform across the cross-section. This is also the autogenous shrinkage that we're not accounting for if we just have a spray-on film, because it's not due to evaporation. It's due to chemical shrinkage and self-desiccation. And the other thing I want to point out is if you add this 250 in here, this line becomes really flat. Right? We see that shrinkage is really not as related to water to cement ratio as this graph would lead us to believe, but it's really more related to paste content and water content. And as a lot of people go to get these higher strengths, they increase the paste content, which means they're going to increase the shrinkage in the overall system. So the big thing I want to drive home here is high-performance concrete something we shouldn't be striving for? No. But what we need to understand is, as we go to higher strength concretes, modulus goes up, which is not necessarily a good thing. Creep goes down, which is not necessarily a good thing. The shrinkage doesn't necessarily decrease like we think that it may, and the material becomes more brittle. So we have a system that starts to become more susceptible to potential early age cracking. Now, I'm not going to talk about this temperature part quite yet. I'm going to talk about it in a second. But what I want to do is, for the concretes that we're looking at, this is the shrinkage that we're seeing in the plain concrete. Again, by the time we get out to about 6 days, we've got 300 microstrain of shrinkage that's built into the system. This is the internally cured concrete. And as we talked about a little bit earlier in the session, this is really, this reduction in shrinkage, this slight expansion, is due to the fact that we're moving water from the lightweight aggregate into the paste. We're keeping the pores inside of the paste full. And by keeping the pores inside of the paste full, we're not getting capillary stresses developed. Those capillary stresses are really what's responsible for the macroscopic shrinkage that we see. So we could actually say that the shrinkage of the paste is related to essentially how wet the concrete is, the degree of saturation, but it's also related to the size of the pores that are empty. So if we keep all the pores full, we keep the bigger pores full, we can substantially reduce the shrinkage, which is what we're seeing on this plot back here. In the internally cured concrete, we're seeing a slight expansion due to swelling at early ages, and then really no shrinkage during that first week that concrete's being placed. Now, what are some of the benefits of this when we start to look at other properties of these decks? Well, one of the things I want to talk a little bit about very briefly is some of the way that this also contributes to some of the thermal effects that we may be seeing. So in addition to using the rings just to monitor drying shrinkage or just to monitor autogenous shrinkage, what we're actually going to do is we're going to use a test here where we're going to restrain the concrete, and then we're going to also try to send the concrete through different temperature cycles. And what we're really looking at here is sort of a twofold issue. One, if we drop the temperature, we can see how much residual stress capacity there is in the system, how much we have to drop the temperature to make it crack. And if you're thinking about this in sort of a really practical sense, this is the question we're trying to answer a lot of times in 2 or 3 days. We start to remove formwork, we start to remove some of the curing blankets, we start to do some of those things. What happens now? How much of a temperature drop can we sustain before we would get cracking in those particular elements? Now, this looks like a ring test here, as we've seen talk about the ASTM 1581. There are 2 main differences with this test. One, you will notice that this particular test has 2 rings. It's got an inside ring and an outside ring. The inside ring is for shrinkage. The outside ring is for expansion. And as we mentioned before, you can get a little bit of swelling in these mixtures. All right, and that's one of the things we want to try to capture. The other thing that I want to point out is these rings are not made out of steel. These rings are made out of a special kind of steel called Rebar, which doesn't change dimension very substantially as the temperature drops. So the restraint is staying constant, and we're dropping the temperature, so the concrete will be what's wanting to move during that particular test. So a typical result that we may see for some of these concretes that we're looking at, and we'll talk as we go through, we'll essentially be comparing a plain and an internally cured system. The basic idea is the plain system, we can see we cast it, the stresses build up slowly over time. At 3 days, we can see they rise quickly, and the reason they're rising quickly is because we're dropping the temperature right around the 83 days. What's interesting about this plot over here is we drop the temperature 10 degrees Celsius, roughly 20 degrees Fahrenheit, and the system cracked. If we do exactly the same thing with the internally cured mortar, we take the system, we see that we're getting some stress buildup, but not nearly what we saw in the plain system. Now we drop the temperature right around 3 days. What we see is a substantially higher amount of stress can be tolerated in the system. Instead of having a 10 degrees Celsius or 20 degree Fahrenheit temperature drop, we now have a 27 degree temperature drop that's required to cause cracking. So all of a sudden we've got a system that's a lot more robust to cracking at these early ages. And one of the real reasons that this is very important is because we have big temperature differences that are taking place in samples. One, because of the fact that we're losing heat to the atmosphere, but also we have heat and hydration buildup in the samples as well. So building in a little extra capacity really can help us out substantially. The other thing that I'll point out is the stress development rates in both of these systems are not the same. This is partially due to the fact that you've got a system that's more saturated, and it's partially due to the fact that you've got a system that has a slightly lower elastic modulus, because we've got the lightweight aggregate system. So all of a sudden now we can actually be even reducing the rate of stress development because the coefficient of thermal expansion drops with increasing degree of saturation, and because we've got a slightly more compliant system. We can actually go through and do this type of testing at different ages, and we can really trace out some envelopes that give us the overall reserve capacity in those systems, so we can see how much additional loading or temperature swing we may be able to tolerate. Now what I want to really do here is I want to take what I think is sort of a next step forward, and where we're really trying to bring 2 things together. We're trying to simultaneously look at shrinkage and corrosion effects at the same time. So really the idea here is we know that internal curing is effective at reducing the shrinkage. We talked a little bit earlier that it's effective in reducing transport properties, and we'll see this later on this afternoon. There'll be several talks that start to talk about this. And what we want to do is we want to use a full-scale slab geometry that's instrumented with an instrumented rebar to start to look at how the corrosion is taking place in these 2 systems. All right, the results are aimed at really starting to understand a little bit better how internal curing is really going to alter service life, because neither one of these components on its own starts to fully capture the behavior. So the idea here is we're going to place a plain and an internally cured system, and those are the 2 systems I'm going to be talking about today. They're on a restrained element. This is roughly 14 feet long, 5 meters long. It's a fairly substantial beam that's underneath here, and I'll give you the dimensions in a second, but it's a very, very, very stiff element. So we've got a high degree of restraint in the system, and we're going to place an instrumented rebar right down the center here. so that we can actually start to monitor a few things about corrosion. So as I mentioned, here are some of the details. It's a heavily instrumented W12 by 210 beam, so this is a very, very stiff beam. It's widened at the ends and it's deepened at the ends to make sure we have sufficient restraint. We bolt and tie down the ends of this. And in this particular case, since we're using the instrumented bar, we put slight wedges in the center, because what we want to be able to do is control where the crack is going to form if it does form. And one of the things we're really looking at is not only the width of the crack that forms, but we think that one of the most important things is, in addition to the width, is how much debonding we get along the length of the bar. Because if we get debonding along the length of the bar, chloride ions can move very quickly along the length of the bar and start to corrode a substantial length of that bar that's taking place in the system. So, as I mentioned before, it's an instrumented rebar. So what this means is we've taken a number 6 grade 60 rebar. We've essentially put that into the center section, and we've threaded the ends. This 15-inch section of the rebar has actually been hollowed out, so we've drilled out the center portion of that rebar, and we've placed in these different small sensors that will actually be ground so that they're flat on the surface, and we can monitor the corrosion at those particular pins, so we can see how far back away from the surface that corrosion is starting to take place. The whole idea here is we hollowed this out and we tried to keep the minimum temperature steel that we would have, so that we've got about 28 sensors that are spaced about every inch apart as we work our way away from the surface of the crack. Again, we're going to be doing corrosion monitoring in here, so we're going to be using a reference electrode. We're using a stainless steel reference electrode that for the duration of this test has remained relatively stable. And what we're going to do here is we're going to talk a little bit more about some of the results. So one of the things that I really want to point out, probably the first thing that's the most notable here, we can look at the green line, we can look at the blue line. The green is the internally cured mix, the blue is the plain mix. The internally cured mix is under a slight compression because of that expansion and that swelling. The other mix is undergoing tension. The green mix, you can see a little bit of swelling here due to swelling and plus due to temperature, but the stresses are slightly in compression. They remain there throughout the entire test. Right after, I believe it was after about 2 weeks, we started to dry these elements out. Right? The blue one, though, you can see there's several of these jumps in the data. You may say, oh, there must be something funny happening in the data. Well, those jumps are something funny that's happening. Those jumps are cracks. And what's interesting about this is the gauge section is about 8 feet long, and we picked up at least 3 cracks that formed in that 8-foot section. So about every 3 feet long, we're getting cracking in the system. And what's interesting really about this is we set this up so that we can actually monitor the cracks that we're developing, monitoring the width of the cracks. Here you see the first crack that's developing. As the second crack starts to form, we see the crack gets a little bit narrower and then starts to pick up again. The next crack forms. We can sort of see this repeated pattern. The second and third cracks we're not monitoring with the continual monitoring that we're using here, but we're just monitoring the widths that are forming. So we get a fairly safe or fairly stable size of the cracks that are forming in the system. The other thing, though, that I want to point out that this really doesn't capture, this gives us a crack width, but it doesn't give us how much of the bar is debonding, all right, when that crack starts to form, and how much of an opening is happening in that system. So as mentioned, we're going to be monitoring corrosion in the system. We're going to be using the sensors. We're going to be using half-cell potential, and then we're doing additional chloride testing. The basic thing here, as I mentioned before, after this two-week period, we then went in and we actually ponded over top of the center portion of the specimen. This pond was slightly larger, but the basic idea is we were supplying this de-icing salt. What was really interesting about this is the internally cured concretes were 2.5, 3 years later, they're still not undergoing corrosion. The main reason that they're not undergoing corrosion is because we've got a fairly decent cover thickness on them. The chlorides are working their way down to the bar. There's no cracking in that system. The plain system, however, right, has that crack, and we can see that the sensors start to go into corrosion almost instantly. And what's really intriguing about this, and what's really sort of backs up some of the other work that we've been doing on this, it's not just corrosion taking place at the crack. We've got corrosion that's taking place substantial distances away from the crack surface, mainly because we're getting debonding in those areas as this crack forms. So the crack just doesn't go down to the bar and stop. The crack goes down to the bar, and we start to get debonding along the length of the bar, and that comes a fairly substantial component of this. Now, to bring this back and to sort of tie this back into some of the field things that we had mentioned, as I mentioned before, we're really trying to understand the interrelation between restrained shrinkage, the stresses that develop in cracking, as well as corrosion. Here's a little bit of information on the chloride ingress, basically just looking at penetration depth. And as I mentioned, this afternoon there will be several talks that get into all kinds of transport properties in a lot more detail. One of the things that we're seeing is because of the increased hydration, because of the disconnection of the interfacial transition zone, we're getting lower, less chloride transport in the systems that are internally cured. This, again, for this particular system, gives us a little bit of that information. Now, how does this start to relate to some of the things that we're seeing in practice? Here is an example of two bridges that have been cast. These bridges were cast at the same time. There was a day separating the two. Same contractor, same raw materials, same construction crew that was placing these. But we have a plain bridge deck and an internally cured deck. Now, the strength of the plain system was again about 10 to 15% higher. The transport properties of the internally cured system are slightly lower in that system. They're about 10% lower. But what's really the evidence that is really driving us to the idea that this has the potential to change service life is what we observe going back to this bridge deck as we keep going throughout time. The plain deck has 3 cracks that are formed, and the cracks, I would say, are substantial width. The internally cured deck has no cracking. Now, does this mean that you should expect no cracking on every internally cured bridge deck? I would say no, that's pretty unrealistic. But what we can definitely see here is there's a substantial reduction in the number of cracks that are forming in those particular cases. Same crew, same plant, same location. The only thing we did was we replaced about 25% of the lightweight, or the sand with lightweight aggregate. Okay. So in conclusion, the whole thing has really been focused on the idea that lower water to cement ratio, high phase mixtures can be more susceptible to cracking. This is due to autogenous, drying, and thermal shrinkage. By using internal curing, it allows us to reduce the autogenous shrinkage. It increases, by reducing the autogenous shrinkage, we increase the stress capacity in the system, which means that we have a little bit more robustness when it comes to thermal cracking. We have a little bit more robustness when it comes to loading, and it may allow us to make it through that first 2 to 3 week period a little bit better. Internal curing reduces the transport. We've begun a program looking here at these large-scale slabs to simultaneously investigate cracking and transport to bring those two things together. The instrumented rebar has helped us because it's not only determined the age at which corrosion is beginning or the fact that we're getting corrosion in the system, but we're also able to see things like the distribution along the interface, which can be substantially further back from the crack than originally thought. The plain mix, the takeaway here is it cracked at several locations, went into corrosion very quickly. The internally cured mix didn't crack and is still being monitored for corrosion. So with that, I'll turn it back over to Anton.
Thank you, Jason. We have time for a few more questions. Any questions from the audience? Go ahead, please come forward.
In your studies, by the way, excellent presentation. What would you say is the optimum mix with regards to the lightweight aggregate? And the second question is, by using internal curing, can we reduce the thickness of the concrete? Is it advisable or?
Well, okay, so there are a few ways to go. I mean, when we talk about what is optimal what I would say here is we can use a wide variety of internal curing agents to get what we want to get. We have found success in using a wide variety of lightweight aggregates, extended lightweight aggregates. As I mentioned, we tested all of them. The difference is you use a slightly different proportion of the aggregate based on absorption capacity. You may originally think that a low absorption aggregate is not as good in that case, but that doesn't really bear out because what you end up doing is using a little bit more of it, but it's better distributed throughout the system. So it's it forces you to get a system that's more well distributed throughout the case. So I wouldn't make an argument that a 12% aggregate is a lot better than a 14% aggregate, or I don't think it's there. and I'll let the sales guys who sell 12 and 14% aggregates fight with each other about that. I think all of them work. Where I think really the sweet spot is in this is you can go to these higher performance mixtures because you have the benefit of the internal curing. So now you can conveniently, safely put out something that's like a 0.36 with the silica fume, so you can really reduce your transport properties. You're not as worried about your thermal cracking, your autogenous cracking, because you've essentially taken the autogenous part of this off the table. Could you reduce the thickness? I think it would be possible to start reducing thickness, but it depends on what your limitations are. If your thickness limitation is really driven by cover depth, then you've got to do your calculations to figure out, if I've got a concrete that's more dense, how does that relate to a 0.45 water to cement ratio? There's something you can gain there, but that's not the direction that we've really looked at. We've been really saying, can I take a bridge deck that's being replaced or being resurfaced at 25 years and make a 60-year solution? That's really what we've been looking at. It's interesting. Thank you.
Any other questions? Go ahead.
What I think was a very interesting presentation. And you point out something that really moved me is when you're talking about the transportation of the chlorides versus the transportation of the chloride, through the mass of the concrete versus the transportation through the cracks and through the perimeter cracking that was found by Otto in the 70s. And I think this is a wonderful finding that I recommend you to go ahead and if you can talk a little bit more about that, I would appreciate it very much.
Yeah, actually, where we started to look at this issue, and we've been looking at monitoring crack widths for quite a while. And what we really started to do is we were doing some work with the Danish Technical University, and we were actually able to start to image what was happening along the bar. And what's interesting is we focus a lot on the width of the crack, but really where things start to get interesting is where you get the width of the cracks, starts to stay stable, but you start to get that debonding. And that's where we really started to develop this idea of using the sensors along the bar, because this starts to explain a lot of things that we can't explain just by looking at crack widths. So you can have two crack widths with different covers. The crack widths are the same, but you have completely different behavior. One of the reasons I believe is likely this debonding. And this debonding, I think, is really important because it allows, the first 2 or 3 times we saw the data, it's a substantial distance that the chlorides are able to migrate along the bar.
That was going to be my second question. How much is the debonding with respect to the diameter of the bar or whatever?
Yeah, well, in this case, it's a little bit of, it's a small sample that we're looking at because you may or may not realize drilling out those bars and placing those in, that's not something we're going to be doing on a lot of bridge decks because it takes a little bit of time. But almost every time we see about at least 4 to 6 inches at minimum, and even more coming back away along the way. But it also depends on the load that this, if the loads are staying, the stresses are staying low, it's possible that the crack just goes to the bar, slight debonding. But in the case we were looking at, there's a lot more debonding taking place. And we've got a study right now to look at how the stress level and crack width all relate to the debonding.
So we can imply also that the age, the crack will continue to vary.
I'm not going to say they're going to continue, but I know they're not going to go backwards. Right? So it's only going to get worse over time.
Any other questions? One last question. You're in.
I'm trying to understand creep and modulus at very early ages. At what age do creep and modulus actually, show a difference, or a significant difference in a high-strength mix compared to a normal mix?
Oh, well, the differences are sort of built into the system. You've got a system that's much, if you're comparing a 30 MPa mix with 100 MPa, you've got different moduli from very early on because you've got more of the system that's dense, more of it's hydrating, so the modulus is very different at those early ages. And the thing that I think is really important in this case, I know when I went through my undergrad, it was sort of driven into your head, low creep, low creep, low creep, because you're typically looking at column shortening and things like this. In this particular case, creep is not necessarily a bad thing. We take advantage of its ability to relax stresses out of the system. So when we go to the higher strength concretes, we've made it more stiff so it's less compliant. We've got to get more stress into the system to maintain zero displacement. and then we don't get as much relaxation. But the high modulus takes place right from the beginning. So some other ways that you can go about altering some of these properties are to use materials that don't react as quickly. So you start replacing some of your cement with slag, you can slow down that development and take advantage of some of that. But that's an alternative approach to this, but it's a very good approach.
Thank you very much.